Yes, my dear friends. Now, in this particular part, we are going to discuss about the plane of symmetry. Now, what is a plane of symmetry? As you can see over here, it's an imaginary plane which is passing through the crystal, and it divides the crystal into two parts, such that the one part is the exact mirror image of the other part. This is a very important condition. Not only should divide the crystal into two parts, but at the same time, the two parts that we get should be the exact mirror image of each other. Then only I can call that particular plane as what? Yes, plane of symmetry. Now, when we consider cubic geometry, my dear friends, remember there are two types of planes. One is called as a rectangular plane, the other is called as a diagonal plane. Now, if you remember, crystal lattice is three-dimensional. So when we talk about a rectangular plane, so these are the three rectangular planes, my dear friends. Okay, so one is going to be along y-axis, other is going to be along x-axis, and the other is going to be z-axis. Now the shaded portion, can you see? Okay, this is going to be the planes that I am referring to. Okay, this plane, and this plane. Okay, so these are three rectangular planes. Now when we go into a diagonal plane, as I said, there are two types. So this is a diagonal plane. Diagonal means what? Connecting the opposite sides. So this is connecting the opposite sides. So this is called as a diagonal plane. Now how many total numbers are going to be there? Okay, so rectangular planes, 3. But when you talk about a diagonal plane, they are going to be, I give you a very simple formula as far as a cube is concerned, my dear friends. And that is, whatever the number of faces are, that many diagonal planes are there. So when there are going to be 6 faces, I have already explained you this, isn't it? So when there are going to be 6 faces, so there will be 6 diagonal planes. Okay, so 3 rectangular planes and 6 diagonal. Okay, so this is about you need to refer to when the question is said on plane of symmetry, what exactly a plane of symmetry is, and the most important, my dear friends, diagram. I hope you have understood this very well. Yes, my dear friends, now we will discuss about law of rationality of indices. Alright, now what it says is, I'll first of all read out and then I'll explain it. It says that it is possible to choose along the 3 coordinate axes. There are 3 axes, x, y, and z. So 3 coordinate axes, unit distances. Now the unit distances are what? A, B, and C. X axis A, y axis B, and z axis C. Which may or may not be of equal distances. Because we are not talking about center of symmetry over here. So either the distance can be same or it can be different. Such that the ratio of these intercepts of any plane in the crystal will be given as what? MA is to MB is to BC. Now what are these M and P? M and P, my dear friends, are integral numbers. And these integral numbers are known as weiss indices. Okay, what are they known as? Weiss indices. Now, my dear friends, there is another concept also, and that is called as Miller indices. Now, how you can calculate Miller indices on the basis of weiss indices, I'll tell you that it's a very easy technique, and that is technique number 1 is what you do is that when you already have a weiss indice, isn't it? So that weiss indices has to be converted into the next part, and how you do it? By multiplying by the LCM. Alright? So here I give you a heading, and that is determination or calculation of Miller indices. So first thing is reciprocal of weiss indice. That's step number 1. Next, multiply by the LCM of the weiss indices. And the third option, convert it into the simplest ratio. And once again, explain you the 3 steps. You already have weiss indices. What are weiss indices? I have already explained it. You take the reciprocal of the weiss indices. That is step number 1. Next, what you do is you multiply those reciprocal, whatever you get, by the LCM of the weiss indices. I hope you know how to calculate the LCM. And then the third one is optional. Okay, sometimes we have to convert it. Sometimes whatever the answer that you get after multiplying by the LCM, that itself is the Miller indices. But sometimes we have to convert it into the simplest ratio. and that is what we get the weiss indices from this particular part. So this is about the calculation of Miller indices. So my dear friends, these are the 2 points that you need to remember, and that is from the law of rationality of indices, you come to know about weiss indices, and then these 3 steps by means of which the weiss indices can be converted into Miller indices. You don't worry about it. What I do is I give some examples so that you exactly understand how, because this is theoretical explanation. Now I'll give you examples on the basis of which you can easily understand that yes, how this weiss indice can be converted into Miller indices. Alright? I hope you have understood up to this. Yes, my dear friends. Now, as I was telling you, I'll give you examples so that you understand how the weiss indice can be converted into Miller indices. Okay? So, weiss indice we have 1:1:1. So, you take the reciprocal, you get the same 1:1:1. The LCM of this is also 1. So, you multiply each of this by 1. So, once again you get the same 1. And that is the Miller indices. Okay, the same indices. So, most of the cases the weiss indice is equal to Miller indices. That's why purposely I give you this particular example. So, they can be same also. One more important point is the Miller indices are represented by H:K:L. Okay, remember this indice it was M:N:P. Okay, so here it is H:K:L. We're going to do 2:2:2. So in this case, when we take the reciprocal of this, so it is 1/2, 1/2, and 1/2. The LCM of this is 2, so multiply it by 2, so you get 1:1:1. Again, once again, it is almost in the simplest ratio, so this gives you 1:1:1. Alright? Next part is 2:3:3. So we make it as half, 1/3, 1/3. The LCM of this is going to be 6. So we have 3:2:2. So this is also 3:2:2. Next is we have got 2:3:4. So half, 1/3, 1/4. The LCM is 12. So this will give you 6:4:3. Okay, so the same we will be having over here also because they are all in the simplest ratio. Next is half is to 1:1. So we have 2:1:1. The LCM is also 2. So what we do is over here is 2. We go for 4 into 2. So if you go into the simplest one, we have 2:1:1. 1:1 is to infinity, 1/1. So that is going to be 1. This is going to be 1/infinity. So when you calculate by LCM, so this is going to be 1:1 is to 0. Because 1/infinity is 0. So you get the same answer, 1:1:0. Okay? So this is, my friends, few examples whereby the weiss indices can be converted into Miller indices. I hope you understood this. Yes, my dear friends, we now go into the next part, that is different types of planes. So here I have shown the diagrams, so you understand very well. The 3 axes, x, y, and z. We start with the first one. You see the shaded portion of this one. It has an intercept only on the x-axis. It is parallel to the y and the z-axis. So when you go for weiss indices, I will write it down as W1, it will be 1 is to infinity is to infinity. This is x, we consider as unit distance, y and z, they are parallel, so it is infinity. If you convert this into Miller indices, we have 1/infinity is 0, 1/infinity is 0, so 1 is to 0 is to 0, that is the Miller indices. So therefore, the plane that we call it as 1, 0, 0 plane. Okay, this is designated as what? 1, 0, 0 plane. Now, if I am going to change the axis, or if I consider this plane on any of these axes, then the possibilities that we have is, okay, and then the other possibility is 0, 1, 0. And next is we have 0, 0, 1. Now what does this mean is, here I had an intercept only on the x-axis, parallel to y and z. Here it is parallel to the x and the z, only having an intercept at the y-axis. And here it is parallel to the x and the y, only having an intercept at the z-axis. So these are the three possible combinations that we have for this first plane. Alright, we go to the next one. You can see we have an intercept that is A along x-axis and B along y-axis. That means it is parallel to the z-axis. Okay, so when we go for the weiss indices, what we have is 1 is to 1 is to infinity. Okay, this is what we get. I convert this into Miller indices, it will give me 1 is to 1 is to 0. Okay, so this is called as 1, 1, 0 plane. Okay, now I got some combinations. What that combination is? I can have 0, 1, 1, so it is parallel to the x-axis. I have 1, 0, 1, so it is parallel to the y-axis. So this is parallel to z-axis, parallel to x-axis, parallel to y-axis. So these are the three possibilities that we have. Okay, and finally now we go over here. We have A as intercept on the x-axis, B as y, and Z as C as on the z-axis. So it's not parallel to any of the axes. So we have this indices, unit distance is 1 is to 1 is to 1. And I've already shown you, so the middle indices also will be the same, and that is 1 is to 1 is to 1, and therefore we got this plane as 1, 1. Right? Okay, we don't have any other options over here because it's not parallel to any of the axes, so it is called as 1, 1, 1 plane. I hope you have understood the different types of plane.